Okay, hey, hello everyone. I'm just making another short video, little instructional video showing you how to run a simple linear regression analysis in SPSS. So I've got a data file open on my screen, which you can see hopefully, and this is a data file that we're going to use in the exercise sheet this week. It's called tmakesyourainy.sav. The SPSS data file, and this is a data file. I think it might be data that has come from the Andy Field textbook, but it's been amended. And the basis of the analysis we're going to run and this kind of data set is the idea that we're going to look to see if we can predict someone's cognitive function, how well they're functioning, based on how many cups of tea they drink. So I think the general idea is the more cups of tea you drink, probably the more caffeine in your system, the more alert and the better your cognitive function. So probably a made-up data set, not real research in any sense, but useful to illustrate how we would run a simple linear regression. Okay, so quite straightforward to do that with this data. We're going to just click on Analyze, Regression, and it gives us a number of options. The one we're looking at is linear, straightforward linear regression. Okay, brings up this pop-up box for us, and there are a number of fields for us to populate. One's the dependent variable, the other's the independent variable. So in this case, the thing we're interested in measuring the outcome, the dependent variable, is cognitive function, how well someone is functioning cognitively. And the independent variable, the thing that we are measuring as our predictor, is number of cups of tea drunk. Okay, so I moved our cognitive function to the DV box and number of cups of teas to the independent box. And you can see it's got independent and an S in parentheses next to it, so we could have more than one independent variable. If we did, that would be a multiple regression model, and that's something we'll come onto in week 11. But for now, we've only got one independent variable, one predictor, and one dependent variable, one outcome, the thing we are trying to predict. Okay, so to set this up, there's a couple of other things to do. We're going to click on Statistics. This brings up this other pop-up box, and there's a couple of things by default that are already selected. One's Estimates, and that gives us our regression coefficients, so we want those. That gives us the value of alpha, the intercept, and beta, the slope of the line. Model Fit is also selected, and one other thing that would be useful to have is descriptives, so we'll select descriptives as well. Click Continue. One other thing I'm going to ask for as well, whilst we're in this particular area before we run the analysis, is a plot. So I'm going to ask for a plot for us to just eyeball quickly and have a look at. We're going to ask for a plot for standardized Z scores of the residuals. So the standardized residuals against the standardized predicted scores for those residuals. Okay, so we're going to put Z score for the residual in the Y box, and Z for the predicted in the X box, and click Continue. And then I'm just going to click OK and run the analysis, and that's going to give us, as ever in SPSS, it's going to give us plenty of output. Okay, so it gives us, firstly, it gives us a table of descriptive statistics, relatively minimal use at the moment. That's first table. It then gives us another table which is correlations between our two variables, and this is kind of useful to just look at quickly. What we can see is we've got a Pearson's correlation between cognitive function and number of cups of tea drunk of 0.078. It's quite a small correlation, but if you look at the significance underneath, it's got a p-value of significance of 0.019. So we've got a statistically significant positive correlation, albeit a small one. And that's useful to know when we're looking at regression, because as you know from correlation looks at the linear relationship between two variables as well, how they're related. and it gives us an indication that we might find, if we've got a significant relationship, a significant correlation, it gives us an indication that our variables might be related. We might find that we can use one to predict the other. This next table here is just tells us which variables were entered and which is the DV, which is the IV. Then after that, we're getting onto the useful tables really for interpreting a regression analysis. One's the model summary table, the next is the ANOVA table and the coefficients table. I covered these in the lecture. As I said, the ANOVA table, which is the model fit essentially, and the coefficients table are the kind of two best ones for summarizing whether the regression analysis is useful. We get a little bit of useful information from the model summary table in terms of effect size. We'll come back to those in a sec, but we'll just have a quick look at this scatter plot I asked for and talk about that. So what we've got here is standardized residuals. So remember, the residuals are the errors between the actual and predicted values. So we've got standardized residuals on the y-axis, standardized predicted values on the x-axis, so they're measured on the same scale. And what we're interested in on the y-axis, we've got this 0 in the middle. This is our reference point. So the closer to that 0 line a point is, the lower is its error. And what we're looking at here, there are a number of assumptions that you kind of need to meet in order to do this type of parametric statistical test, such as a linear regression. You want your variables to have a linear relationship, otherwise you're going to get erroneous results. And you also want fairly, for the whole length of the measurement of a particular variable, you want the variance, the variability, to be fairly even. Okay. So the useful thing about this plot is when we look at it, what we're looking to see is, have we got a fairly even spread of points above and below the line? And in this case, it looks like we do. So that's pretty useful. We want an even enough spread. If all the points were above the line, or all the points were below the line, or a lot of them were above it, we'd be able to see some deviation from kind of a linear relationship, possibly, or maybe some sort of weird pattern that tells us the relationship's not linear. That the lower predicted value scores kind of were above the line, but in the middle they were below it. Maybe we've got some U-shaped pattern going on, and that's going to tell us that we've not got a linear relationship. It looks like we do in this case. They're pretty fairly evenly spread out above and below that y equals 0 reference line along there. Okay, the other thing we can look at when we look at this is we can look for outliers. So if you recall, like when we're looking at outliers, they're things that are going to be greater than or less than 3 standard deviations above or below the mean. So if they're 3 standard deviations above the mean or below the mean, then they're in the kind of 0.001, like the 1 in 1,000 type of score. So in this case, we've got one that's quite close to 3 standard deviations, but there are few, if any, outliers. And if we do have outliers, it's not too much of a problem. Extreme scores can, though, affect whether they can affect where the regression line is fitted. So if we had one really extreme score or a few, it's going to influence the slope of the line. So we need to be mindful of that. In this case, this data looks pretty fairly even. Few, if any, extreme scores that are going to influence where that regression line is going to be fitted. Okay, so let's go back and look at the actual output then, the results. So I always think the first thing, once you've visualized, have a look at the visual representation, such as that scatter plot, to make sure your assumptions are fairly safe for running this type of analysis. One of the first places to look then is the ANOVA table. So the model fit, how good is fitting the regression line? Does it provide a better model for the pattern in the data than just using the mean score of the y variable? So If you remember in the lecture, what I mentioned was that what this table is showing you is that a null hypothesis statistical test has been conducted using ANOVA, comparing two things. It's comparing whether the slope of the regression line that we fitted is significantly different to 0, and the slope of the mean score of y is 0. It's a completely flat line running along from the mean score on the y-axis. Yeah. So if we get a significant f value, a significant ANOVA result in this table, it tells us that fitting the regression line has explained more of the variance, so it's provided a better model of the data than just using the mean score on the outcome variable. Okay, and you can see in this box we've got an f value of 4.331, so it's more than 1, it's likely to be significant. It tells us that the between groups variability is greater than the scatter around groups, and we've got a significance value of 0.038. Okay, so it is, if we round that to 2 decimal places, that's 0.04, so it is a statistically significant result. So fitting this model, fitting the regression line, has explained more of the variability in the data than just using the mean score of the y variable. Okay, so it's a better model than just using the mean. So moving on from that, the next thing that's worth looking at is the coefficients table. Hopefully you remember from the lecture, this provides us with a couple of useful bits of information. So the first thing to look at is this unstandardized coefficients, these first two columns, and the one we're interested in is the one labeled B. It's got a capital B above it. It gives us two numbers, one for the constant, which remember is the intercept. That's the value of A or alpha. So that's the value of y when the score on the x variable, the independent variable, is 0. Okay, and in this case the intercept is 49.218, so 49.22 if we round that up, if we're thinking about our regression equation. The other thing it gives us is the number of cups of tea drunk per day. So that is our independent variable, our input variable, and it gives us a score in this B column of 0.46, and that's the slope of the line. So the two coefficients we're interested in for our regression equation are in this column B, this first column, and the constant, the intercept value, and the slope of the line. Okay, so 0.46. Well, that's pretty interesting in itself. What's telling us is that when x is 0, the value of y is about 49.22, and the slope of the line going up is about 0.46. So every unit, remember these are unstandardized, so every unit that whatever our variable on the x-axis is goes up. So in this case, every time it goes up 1 cup of tea, our measure on the y value goes up by half a unit, whatever that might be measured in. Okay, so next thing to look at is we know that fitting the model is better than just using the mean. We know what our intercept is and the slope of the line. What we're interested in knowing is, based on this, is drinking cups of tea per day, number of cups of tea you've drunk per day, is it a good predictor of cognitive function? And to answer that question, we need to look at these last two columns in the coefficients table. That's the t-test and its significance value. Okay, and so what we've got here for number of cups of tea drunk per day is a t-value of 2.081 and a probability of 0.038. Okay, so it is statistically significant. Look, if you notice, the significance is the same as it was for the ANOVA table. What we're getting here is we're getting a separate test that tells us that number of cups of tea drunk per day is a significant predictor of cognitive function. We kind of already knew that from this first table because we got a significant ANOVA result, so it told us fitting the model is better than not fitting the model. Okay, it confused me for a long time as to why. It's if you think about it, really, in effect, the t-test for a simple linear regression where you've only got one independent variable, this t-test is telling you the same thing as the ANOVA test. As a separate test, it becomes more useful when you're doing multiple regression, because you could have another 2 or 3 or more independent variable predictors in this table when you're running multiple regression, and not all of them might be significant predictors of the outcome variable. You could still have a significant model, so a significant f value, but then you would, if you had multiple regression with 3 or 4 variables, you'd then have to come and look at these t-values to see which of your predictors were significant. They all could be, only some of them might be. It works a bit like that. But when you are just running linear regression with one independent variable, one dependent variable, it's sort of duplicating a little bit of information you've already got. And what you would find is doing a slightly different test comparing means. As you know, the t-test and the ANOVA are slightly different. They're comparing groups. But if you took this value of t 2.081 and squared it, what you would actually find is you've got this f value here. Okay, so those are the important things. One final thing, some of the important things. Is the model fit better than using the mean? Yes, it is. In this case, we've got a significant ANOVA. What's the constant? 49.22. What's the slope of the line? 0.46. Is number of cups of tea drunk per day a significant predictor of cognitive function? Yes, it is. We've got a t-value of 2.081. P is equal to 0.038 in this case. One final thing that's worth mentioning or worth looking at is the standardized coefficients. So as you know, these first two columns here, the column we looked at with our B for our slope, that's an unstandardized measure. And as I said, one unit goes up on the x-axis, it goes up by 0.46 on the y-axis. If these are measured in different scales, you know, one could be thousands of miles, the other could be IQ points, something like that. They could be, you know, completely different scales. Cups of tea could be measured on a scale of 1 to 5. Cognitive function could be measured, you know, on scales of hundreds, something like that. So what it's useful to do is look at the standardized coefficient. So by standardizing it, we're putting them both on the same scale, so it's easier to compare how much a change in one influences a change in the other. And you can see here under standardized coefficients, beta is called in SPSS in this table. We've got a standardized coefficient of 0.078. So what this is telling us is that every time tea consumption goes up one standard deviation, then cognitive function goes up 0.078 standard deviation. So only a small amount, so about less than 1/10 of a standard deviation in this case that would be. Okay, so that's much more useful really, and when you've got a number of different independent variables and they're measured on different scales, the change in the slope relating to each of those variables may differ. One may have a higher slope, but when you look at it on a standardized scale, it contributes less to the model. So what this is telling us really is that although we've got a significant model and we can predict cognitive function with how much tea has been drunk, there's a lot of error around the model, and the amount that cognitive function increases is very small as tea drinking increases. And the last thing to look at really then to sort of confirm that is the model summary table. So we've got a significant result statistically, but practically, is it significant? Is it of interest in any way? So the model summary table gives us various measures of effect size. So R squared is probably the most useful here. It gives us a measure of effect size of 0.006. Okay, so less than 1% of the variance in cognitive function is explained by how much tea people drink. So about 0.6 of a percent, something like that. I think it's probably 3/500ths of the variability in cognitive function is explained by number of cups of tea drunk. So differences in cognitive function, obviously there's probably other variables that would need to be added to this model to account for more variability. There's probably other things that are much better predictors of cognitive function. So that's what we're seeing here is using R squared, that we've got this model. It is significant, but it's not a very good model. There's a lot of error, and it doesn't explain a lot of the variance in scores on the Y variable. Quick mention of this third column here, sorry, adjusted R squared. That is a stricter version of R squared that's more useful when you've got, it's based on the degrees of freedom are adjusted, so it's based on the size of your sample that you're using. If you've got a smaller sample, there's a risk of inflating your R squared value, so adjusted R squared is useful in that case. It's about the same for R and R squared. Similar result in this case, so we'd be safe using R squared based on, I think we've got 80 participants, something like that. Okay, no, 716 participants, so quite a large sample, so not something to be worried about. All right, guys, I'm going to stop talking now. Hopefully that's useful. We'll go over this stuff more in the lab class, and we'll look at how you would kind of write up the results for this.